Okay. All right, now we're recording. Okay, so let me just go back up here. All right, so today, April 13th, 2020, the answers to last time's quiz, pretty straightforward. Just all you had to do was name the things that people printed. Okay. All right, so as I started to say before I realized that we weren't recording, so you should all be experts now in creating CAD files for objects like this. But now what do you do with the CAD files? Once you've created them, well, one really nice and easy thing to do is 3D print them. So we're going to talk today about 3D printers, how they work, how do you prepare the CAD file for the 3D printer. And so that's basically the main thing what we're going to do today. And also, I'm going to give you an assignment today that will not be due until Friday. I'll talk more about that later. So there will not be an assignment due on Wednesday. I'll talk more about it later, but it's going to be a major assignment. And it's going to count as a midterm exam. Okay, so make sure you take careful notes or at least watch the recording. All right, so one of you is already an expert on 3D printing. You students, you may not realize how much we teachers, we talk. And this is something that one of you submitted as your world geography assignment to Mrs. Tilden. Okay, Simon, yes, very good. I didn't want to name you by name unless you wanted to be named by name. Oh, wait a minute, that wasn't Simon that said that. Okay, hey, Simon, are you on right now? Let's see if Simon's one of the ones. Oh, too bad, Simon's not on right now. Okay, well, Simon, we're going to talk about you even though you're not on. Okay, so Simon obviously has a 3D printer, and he used it to create some very cool things, which he then submitted to Mrs. Tilden as part of his world geography assignment. You guys see up here in the upper right-hand corner, this little thing here, remember that? That was the nuclear power plant that I talked about last time. When I went into Simon's CAD file, I saw that he had created the assignment that I asked him to create. And also he had downloaded this other thing that was a nuclear power plant. And now I know why it was that he did it, because he was going to 3D print it here. And he's got another thing here. It looks like a tower of some sort, kind of like the Eiffel Tower, but not quite. So these are all things that he created using Tinkercad, and then he printed them. And so what we're going to do today is we're going to learn how to do that, how to take the CAD files that you've created and turn them into objects that you could send to a 3D printer, or there are other ways you can do it too. 3D printing is not the only way to go. All right, so this is a 3D printer. So up at the top here, you have a spool that contains a long plastic wire. It's called a filament. And so the print head right here, it pulls in the plastic, it melts it, and then it deposits it on the table. Now, this print head can move up and down. So it starts off down really low on the printer, on the table, and it just goes through and it puts plastic wherever plastic needs to be. Then it moves up a little bit, puts more plastic, moves up a little more, puts more plastic, and just keeps on moving like that until it has created the object that you wanted to create. Let's watch a video here. Let's take a couple minutes and watch a video of how this works. I need to, let's see, okay, I need to make sure that my computer sound works. All right, okay, so we're going to watch this video here. Everybody sit back. When I start playing the video, if you can't hear the sound, please let me know and I'll see what I can do. But it looks to me like I've got everything set so you should be able to hear the sound. All right, so let's take a minute and let's learn about 3D printers.
Have you ever tried to wish something into existence? Well, we live in a world where you can practically do that now. We're not talking about a magical genie. We're talking about 3D printers. If you can think it, chances are you can print it.
Okay, before we go on further there, I noticed there's quite a bit of lag, which is unfortunate. So you guys aren't seeing the video with its full motion, you're seeing lag. But how about the sound quality? Were you able to hear the sound pretty well there? I need some yays or nays. Okay, good. All right, so let's keep on going. This is a 7-minute video, but I might stop it most of the way through. But let's watch it and let's see how 3D printers work.
From 3D printed sushi to 3D printed organs, here's a rundown on how 3D printing works and how it's changing our lives. You're watching The Deets, a show where we demystify the technologies that are shaping the future. I'm your host, Riley Wynn. 3D printing is one of the most revolutionary technologies of the 21st century. But what you might not realize is that there are tons of different 3D printing techniques out there. Today, we're going to talk about the four most common varieties: FDM, SLA, laser sintering, and PolyJet. There are some other more specialized methods, but these four are definitely the most widely used. Let's start with FDM, which stands for Fusion Deposition Modeling. If you've seen a 3D printer in person, then chances are
I clicked on something that I didn't think was going to affect the video, but it did. So I'm seeing your comments there about the frame rate being like 3 or maybe even 4 frames per second. And yeah, I realize that's no good, but the sound quality is okay, right? You can hear the sound all right, right? So even though okay, good. So even though the frame rate is only 3 or 4 frames per second, we can still watch it and still get good video out of it. So let me go back and restart it here and see if I can get it back to the same place where it was.
Have you ever tried to wish something? Is that there are tons of different 3D printing techniques out there. Today, we're going to talk about the four most common varieties: FDM, SLA, laser sintering, and PolyJet. There are some other more specialized methods, but these four are definitely the most widely used. Let's start with FDM, which stands for Fusion Deposition Modeling. If you've seen a 3D printer in person, then chances are it was an FDM printer. So how does it work? Well, functionally speaking, an FDM printer works a lot like a hot glue gun that's being operated by a robot. Solid material known as the filament goes in one end, gets pushed through a hot nozzle, it melts, and is deposited in thin layers. This happens over and over until a three-dimensional object emerges. So, in other words, FDM 3D printing is basically 2D printing over and over again. Just each time a layer is completed, the nozzle moves up just a little bit, and the next layer is printed on top of it. Then, there's stereolithography, or SLA. Here's a mind effort for you. SLA basically uses light to grow objects out of a puddle of goo. What? Yeah, exactly. SLA machines work by shining ultraviolet light into a pool of photoreactive resin. Any resin struck by the light solidifies and forms a layer of the object you're printing. Generally speaking, these printers can create objects with far finer details than FDM printers. The third variety of 3D printing is laser sintering. LS prints by flashing a high-powered laser over a bed of superfine powder, fusing the particles together to form a thin solidified layer. The machine then sweeps more powder over the top of that layer and repeats the process until the 3D object is complete. This process isn't common in consumer-level 3D printers, but on the industrial side, it's often used to create large, durable objects out of metal. In fact, SpaceX uses this method to 3D print its Super Draco rocket engines. That's definitely a tough act to follow, but we've got one more on our list. Last but not least is a 3D printing technique known as PolyJet. Think of this one as a mix of FDM and SLA. PolyJet machines squirt out tiny droplets of photoreactive resin onto a build surface, and then immediately harden the resin with ultraviolet light. This process is then repeated hundreds of times to create objects from the bottom up. The benefit of this method is that it's crazy fast and super precise. Unfortunately, most PolyJet printers cost tens of thousands of dollars, so they're out of reach for people like you and me. Now that school is over, let's talk about the real world, because 3D printing is used in almost every industry out there. One awesome example is how 3D printing has completely changed the world of prosthetics. The thing about prosthetics is that every limb needs to be customized for each individual, which makes prosthetics difficult to mass produce. With 3D printing though, you can scan a person's body and then 3D print a prosthetic that's tailor-made to fit the unique geometry of their body. There's even a startup called Print My Leg that provides open source blueprints for prosthetics. They allow others to create decorative prosthetic leg pieces that they can make as an extension of their own personalities, no different than getting a tattoo sleeve or choosing clothes that capture some aspect of your personality. That's just the tip of the iceberg though. We're not only printing limbs now, we're 3D printing organs too. Scientists have successfully 3D printed a mini human heart from stem cells. This heart is partially functional and is used for pharmaceutical research. There are a few challenges ahead in making it fully functional, but the scientists are confident that in a few years, this 3D printed heart will be able to function inside an animal or a human. This technology could be used to create thousands of much-needed hearts for transplant surgeries. Enough about medicine though. Let's talk about shoes. Nike is running away with 3D printing technology. The company recently introduced Flyprint, a 3D printed textile upper for your sneakers. It's the first of its kind and it may bring about a new standard in performance running shoes. Because they're 3D printed, the shoes can be rapidly customized and produced for specific sports or specific athletes. And the shoes can be prototyped 16 times faster than traditional shoemaking methods. 3D printing is even making its way into the construction business these days. It takes Extreme Home Makeover a week to build a house, but with 3D printers, you can build one in a single day. Nonprofit startup Icon invests in affordable housing solutions. These houses are 800 square feet and cost less than $5,000. With 3D printing technology, they're able to provide housing in poorer communities cheaper and quicker. But what if you want a boat in the driveway of your 3D printed house? Well, as Vince Vaughn would say, it's not a boat, it's a yacht. Naval architect Greg Marshall wants to start 3D printing super yachts. Marshall says that you could print an entire super yacht in one go, including the interior. A 150-foot yacht usually takes 2 to 3 years to build traditionally. Marshall claims that you could 3D print that same yacht in as little as 90 days. Hollywood has even hopped on the 3D printed bandwagon. Showbiz is using the technology when it comes to set design and prop making. 3D printing allows studios to create custom props quicker and cheaper than traditional methods. Leica, the animation studio behind movies like Coraline and Kubo and the Two Strings, uses 3D printing to create all the set pieces in its stop motion films. Does your mouth water at the prospect of a nice juicy steak? How about a 3D printed porterhouse made using a paste composed of vegetable-based materials like rice, peas, and seaweed? Yeah, no thanks. But that's what a new Spanish startup, Novami, is working hard to bring to market. Left and right, different foods are being printed. Sushi, burgers, the list goes on. These foods aren't being produced just for publicity. There soon could be an actual need for 3D printed food. The global population is expected to grow to an estimated 9.6 billion people by 2050. And some analysts project that food production will need to be raised by 50% to maintain current levels. How we currently produce food isn't going to be able to keep up with that demand. And 3D printed food may be the additional production method we need to keep from going hungry. The really exciting part is that this is just the beginning. The earliest 3D printers were invented just a couple decades ago, and despite the fact that the technology has advanced in leaps and bounds in that time, it's still very much in its infancy. Today, we're printing organs and rocket engines. In another decade or two, there's no telling what we might be able to create. Would you eat a 3D printed steak? Let us know in the comments below. Until next time, I'm Riley Lynn with Digital Trends, and thanks for watching.
Okay. All right, so I realized the video frame rate was pretty bad there, but I trust that the audio was okay and you guys got an idea of how 3D printing really is revolutionizing the world. And CAD is the first step in 3D printing. You've got to know how to CAD something up before you can 3D print it. So you guys now, you should now understand the basics of how CAD works. Now, obviously, there's a lot more really advanced stuff to do, but with just that little bit of basics that you guys have learned, you can do some tremendous things. So let me tell you what you need to do to take the CAD file that you guys created here, and then you want to turn it into a 3D print. Now, those of you that have 3D printers, which is I know 2 of you have 3D printers, you realize that there's an intermediate step where a piece of software called Slicer software has to come in and play an important role. It takes the CAD file that you guys created and it puts it into a form that the 3D printer can then work with to print. Without this intermediate step, it doesn't work. Okay, so the CAD software that we have talked about has been Tinkercad. We've talked a lot about SolidWorks. We haven't actually done anything in SolidWorks, but I know at least 2 of you do know how SolidWorks works. So SolidWorks is a more professional version of Tinkercad, and there are many, many others. Okay, so what we do is we use Tinkercad or SolidWorks or whatever to create a CAD file, which we then export. And in a few minutes, we're going to learn how to go about exporting files. Okay, and we export it into another piece of software called the slicer. Okay, so there are several different slicers. In fact, there's like dozens of different slicers. Don't worry about the names of it there. But what the slicer does is it takes the 3D printed, or it takes the CAD file you created, and it asks a bunch of questions. The most important question that it asks is, do you want to print the object solid, or do you want to maybe leave a little bit of air in between the spaces inside the object? Because if you were to, let's say you make some object, be it a ball or a square or whatever, okay? If you were to 3D print that object solid, it would use up a tremendous amount of plastic, which would cost, it would run the cost up a lot. It would also increase the print time. In order to print a ball about this big, it would take hours, maybe even all night long, if you were to make it solid. And you don't need it to be solid for most applications. In some applications, if your part is going to undergo a lot of stress, if there are going to be a lot of forces acting on your part and it needs to be strong, okay, then maybe you want to spend the extra time and money and make it solid. But most of the time, most of the parts that you're going to make don't need to be strong. And so what you can do is you can put in a fill percentage. So you can see here, let's look at the 20% fill percentage. So you see that inside your solid object, there's actually going to be a lot of empty space, a lot of air. And there are different patterns that you can use. What you're seeing here is a honeycomb pattern, but there are many other patterns that you could use. But basically what they do is they give enough structure so that your object is going to be firm, it won't collapse, but it doesn't waste plastic putting in solid plastic everywhere when you don't really need solid plastic everywhere. So your slicer program is going to ask you, what kind of infill density do you want? Do you really need 100%, or would 70% be okay, or 20%, or what? Most things that you're just going to use for decoration purposes, I would recommend it somewhere between 20 to 30% fill ratio. It'll make your thing print a whole lot faster, I mean like way faster, and it'll also use up a lot less plastic and therefore be a lot less expensive. Okay, so the slicer software needs to take your CAD file and then based on what fill percentage you make it, it then creates the commands that tell the print head exactly how far to move before depositing some plastic, and then move a little more and deposit some more plastic. Okay, so the slicer program fills a very important role. Now, most of you will not need to worry about the slicer program because most of you don't have 3D printers, but you can still 3D print stuff. In just a second here, I'm going to talk about some online services where you can upload your CAD files to this company, and they will then print the object for you and mail it to you. So think of it kind of like Amazon, only instead of you picking out the things that they want to sell, you create the object that you want, you upload the CAD file, they print it for you, and then they send it back to you. So they are the ones that are going to handle the slicer software, and they're going to do all the printing and maintain all the printing. All you have to do is just the CAD file, and it's really wonderful. Now, if you want, you can use these online services, or maybe if you are good friends with somebody who has a 3D printer, like maybe if you're nice to Simon or if you're nice to Mason, maybe they'll do this for you. But again, you have to do the CAD, and then you give them the file, and then they take care of the slicer and the printing. Okay, so the CAD file that you create needs to be saved in a format that the slicer program can read, right? STL is by far the most common format. Now, there are other formats as well. Some of you are going to say, but what about OBJ? I use OBJ. Yeah, okay. But STL is actually the most commonly used. If you save it as STL, then you can be sure that any slicer program can read it. If you save it in another format, some of the slicer programs can read it, but others of them might not be able to. So I recommend STL. And your homework assignment tonight is going to be to create something and save it and or export it as an STL file and then upload it to Canvas. Okay. All right, so what you're looking at right now is one of the online web services that does 3D printing like I described. The company is named 3dhubs.com. I have used them a lot. They're a great company. The price is actually pretty reasonable. Turnaround's pretty fast. And they can print not only, they can do not only 3D printing in plastic, but they can also make things for you out of metal. So let's say that you've got some part that needs to be really strong, plastic just isn't going to do the job. You can create it in a CAD file. You can send it to them and tell them it needs to be made out of metal. And what they can do is they can use their computer automated milling machines and lathes and saws and whatnot, and they can create the thing for you out of actual metal. They can also do sheet metal and they can do injection molding. I'm not going to talk about those right now. We're going to focus in on 3D printing. All right, so the way that that works then is you go to 3dhubs.com and then you select what type of technology you want them to use when they're creating your object. So we're gonna say we want 3D printing, but as I mentioned a minute ago, there are other options that you can use. But let's say we want to do 3D printing. Okay, so you select the technology that you want, and then you upload the file to them. I see we had a question. So Danny is saying, can it be similar to the one you drew for the previous assignment? Absolutely yes. Very, very much yes, it can be. It can be exactly that. Okay, so we've selected the technology, and then we click here to upload the file to them. Once they get the file, then they're going to ask you a few more questions. There are different types of plastics that you could use. Some plastics are a little stronger. So I'm not going to go into the details of the advantages of the different plastics. On their website, they talk about it. PLA is far and away the most common one. The 3D printer that we have at Ames, it uses PLA, and it's a medium grade plastic. You know, there are stronger ones, but it's easy to work with and common. And most things PLA is going to be good. But if you want, there are other types of plastics and resins that you could use with. Okay, and then they will actually give you a quote right then and there. So if this was the file that we uploaded, okay, then they'll say, okay, if you want one of those prints, it's going to cost you $6.95, not counting shipping. Shipping is on top of that, okay? And that's not too bad. I mean, $6.95 for a little piece of custom-made, custom-made part made out of plastic. $6.95 is not bad at all. So at Ames, we went for a long time before we got a 3D printer because I used this 3D Hubs service, and it was actually cheaper because if you buy a printer, it costs hundreds of dollars. If all you want is one or two parts, why buy a printer? Just use 3D Hubs and have them print it for you. So Danny is saying you have to pay that. Well, not to get credit for this class. I'm just showing you what you could do if you wanted to do it, but you are not required to actually print anything in order to get credit for this class. Okay. All right. So if you like the price, then you can go ahead and check it out. Give them your credit card number. They will print it. And they will mail it to you. If you don't like their price, go check out another website. There are dozens of websites out there that can do it for you. And some do it a little cheaper, some have faster turnaround, but they charge more. Depends. And like I said, if you're really nice to Simon and Mason, maybe you can convince them to do it for you. All right. Okay. All right. So let's take something like, for instance, this is what we created last time. And let's say, whoops, okay. Let's say, oh, I want to 3D print that. Okay, fine. How do you do it? All right. Well, if I were to take the file that you're looking at right now, and if I were to just save it exactly as you see it right now, if I tried to send that to a printer, you would have some problems. Let's see, hang on a second here. So Luke is saying before the library is closed, a bunch of them had 3D printers to use. Yes, yeah, that's true. And okay, so David is absolutely correct. David, you have identified the problem. I have a floating part. Okay, so this lid is way up here just floating in the air. If we try to 3D print that, obviously we're gonna have some problems, right? You can't just print out in the air, okay? So what I need to do is I need to take that lid that's floating, I need to put it on the ground, but not only do I put it on the ground here, I'm gonna flip it upside down. Anybody have an idea why I flipped the lid upside down? Okay, yeah, David, you're right. In fact, I am going to do that in just a minute. I am going to remove the chocolates in just a minute. Okay. So the reason why I need to flip it upside down is very similar to the reason why I can't just print it up in the air. If I had this lid oriented the way that it was originally oriented, what would happen is the 3D printer would go and it would print the walls first, and then it needs to print the upper part. And the upper part would essentially just be floating in air. Now, close to the edges, it would be supported by the walls, but you get out in the middle part there, and there's nothing supporting it there, and you're going to have problems. Now, if you have no other choice, there are ways to get around that. The Slicer program can create little temporary structures that will temporarily hold up that lid, hold up the roof. And then after you print it, you have to go in with a knife and scrape away those temporary structures. So it is possible to do it the way, with the lid the other way, but absolutely not recommended. The best thing to do is flip it up this way so it can print everything that's on the table, and then it can, and then it work its way up. It definitely works a whole lot better. Okay, so you need to do that before you send it, before you can export it. And also, so as David said, if we want the chocolates to be removable, we're going to have to remove them. Because if I sent this to the 3D printer right now, those chocolates would be permanently fused to the bottom part of the box, and maybe I don't want that. Okay, so what I'll do is exactly what David suggested. I'll remove them. Okay, all right. Now I have something that I could send to a 3D printer. Now, the 3D printer that we have at Ames, it can only print one color of plastic at a time. So if I sent this file right here to our 3D printer, everything would be printed in the same color plastic, which maybe is okay, but maybe not. Maybe I don't want them. Maybe I want it to come out the way that I've shown it here. I want the box to be red. I want some of the chocolates to be dark brown and some of the other chocolates to be light brown. So what I'm going to have to do is I'm going to have to 3D print them separately. Print the box first, and then after it's done, I pull the filament out and I put in a different color filament. And then I print the dark chocolates, and then I pull out the filament, put in a different one, and then I print the light chocolates. That's the way you would have to do it with the one at Ames. But there are a few 3D printers out there that do allow to have multiple filaments, and so they could print this all at one time, but those ones are a lot more expensive. Okay, so I see a couple comments here. Give me a sec to get caught up on them. So Mason is suggesting that if I CAD the lid to perfectly fit the box, it probably won't fit after you print it. Mason has obviously got some experience doing this, and he's exactly right. One problem with 3D printers is they don't, especially the cheap ones, but even the expensive ones, they don't print it exactly at the size that you want. And so if you're not careful, that the lid is not going to fit onto the box. What you really want to do is oversize the lid just a little bit in order for him to fit. Okay, so David, I have no idea what you mean when you say Samsung Smart Fridge. I'll go ahead and move on. Okay, so let's suppose that you're using the 3D printer that we have at Ames that can only do one color at a time. But I've got this CAD file here that has everything in it. Okay, so what I can do is I can just select the objects that I want to be printed at the same time. So let's say I want to print the box first and I want it to be red. So what I've done is I've selected the one, I hold down the shift key, I select the other, so now they're both selected. And you can see right here, it tells me I've got two shapes selected, okay? All right, so then if you look in the upper right corner of the screen, you see there's a little option here that says export. right? So what you're going to do is you're going to click on export, and then it's going to ask you what format do you want it saved in. And you can see it tells you right here, if you want to do 3D printing, Tinkercad can save it in 3 different formats. STL is the one that I recommend because it's the most commonly used, but OBJ is also used. Some slicers work well with OBJ. And then there's another one called GLTF, which is not commonly used, but it's an option. So go with STL. Now, if you didn't want to 3D print something, if you wanted instead to laser cut something, like let's say you want to take a piece of wood and you want to burn or cut a pattern into the wood or metal, you can also laser cut metal if you want. Okay, the format you're going to want to use for that is SVG. Okay, but let's assume we're doing a 3D printer, and let's just say we're using the 3D printer that Ames has. So STL is the format that we're going to want to use. And by the way, in your homework tonight, you're going to have to create something, and you're going to have to save it as an STL file, and you're going to have to submit it to Canvas. Okay, it has to be STL. I've set up the assignment in Canvas so that if it's not an STL file, Canvas will reject it. So make sure you save it in STL. Okay, so then it will automatically download. If you guys are using Google Chrome as your browser, you'll see down here that it's been downloaded as an STL file, and that's the name of the STL file. The name of the file will be the same as the name of your Tinkercad, the creation name. Okay, so now let's say that we've got an STL file that's just for the boxes. Okay, but now what about the dark chocolates and the light chocolates? I want those too, right? So what I can do then is I can deselect the chocolate box, and I select only the dark chocolates, and then I export those. When you click export, it will only export the things that are selected at the time that you hit the button. Okay, so it'll only export a file that's the dark chocolates. And then I come back and I do it again a third time, where I only select the objects that are the light chocolates. So now I've got 3 different STL files, and I can print them at 3 different times, and I just have to change out the filament each time to be the color filament that I want. So I hope you guys agree that it's actually pretty easy to use a 3D printer, as long as somebody else is doing the slicing for you and somebody else maintains the printer. As Mason can attest, and I'm sure Simon would agree, maintaining a 3D printer is actually a pain in the neck. There are lots of things that can go wrong with it. If you get a little dirt in there, clogs up the nozzle, makes things bad. Sometimes the plastic doesn't stick well to the table, and then your 3D print gets ruined. And sometimes the plastic sticks too well to the table, so then after you're done, getting it off the table is really a mess. So operating a 3D printer is kind of a pain. But if you guys are going to let 3D Hubs or somebody else take care of all those details for you, you don't need to worry about it. Okay. All right. So now we know how to export files. Next, we're going to learn how to import files. But before I do that, let me just pause and see, does anybody have any questions? Any questions about how to export files? And remember, your homework tonight, you're going to have to export files. So make sure you know to do that. All right, I don't see anybody typing any questions. So let's talk about how to import files. Okay, because as I said last time, that's the way most CAD works, is most people don't create everything from scratch. What they do is let's say they're going to buy a gear from one company and a motor from another company. So you go to the website for the company that makes the gear, and they will have pre-made CAD files already sitting there waiting. You can download a CAD file that is exactly identical to the gear that you would buy from them. And then you go to the company that sells the motor, and on their website, they will have CAD files that you can download. So all you have to do then is take these pre-made CAD files and put them together with some other stuff that you add, and you have a creation. So you don't have to do everything from scratch. Okay, so as you can see here, there are literally hundreds of websites where you can go to where they have things that other people have created that are really amazing. In many cases, super amazing. They put a lot of time into creating these, and you can just go ahead and download them. So grabcad.com is a great one, especially if you're using SolidWorks to do professional level stuff. Gradcad.com is great. But if you're using, or actually for any of these are all pretty good, but you do have to be careful because Tinkercad is very limited. Tinkercad can only accept STL files and OBJ files. And so when you go to these websites, you're going to find that they have a lot of stuff on there, but it's not in a format that Tinkercad can read. Now, SolidWorks can read it. SolidWorks can read anything. Okay. And so Aaron is saying that he's used Thingiverse before. Yeah, I'm sure that many of you have. So just make sure that what you download is in a format that your CAD program can read. And remember that Tinkercad is a very simple program. It can only read STL files and OBJ files. So be careful of that before you go downloading files. Okay, there's another place where you can get files, and that's Canvas. What you see on your screen right now is an assignment that I uploaded to Canvas last night, and I made it so that you guys couldn't see it until now. But if you were to go on Canvas right now, you'll see that this thing is now visible. And this is the instructions for tonight's homework. And you'll see that I've put a couple of files on here that if you click on these files, then they will download to your computer. And these CAD files are the files that you're going to use in the homework tonight. Basically, there are 4 different CAD files for these 4 different gears that you see. And there's a CAD file for the shaft, and there's a CAD file for a thing called a coupler. So does anybody recognize this here? I mean, you guys have played with Legos, right? Any of you when you played with Legos, did you have the Lego gears like this, where you can take a gear like this, and you can fit it on a shaft like this, put it through a little hole like this. Okay, so you put that through there, put the gear on the shaft here, push it on down, and now we have a nifty little thing here where if I turn the crank here, you can see the other one goes around. You guys have ever play with these? The standard Lego sets don't have them, but if you pay the extra and get the expensive Lego sets, they have these. Okay, so this is what we're going to use. So I went and I found, on GrabCAD or Thingiverse or whatever, I found where somebody had created a CAD file that matched these little Lego gears, and there's big ones and there's small ones. Okay, so I have downloaded the CAD files for these Lego gears, and also I downloaded the CAD file for these shafts. And this little thing right here is a coupler. Actually, okay, this is a coupler. Okay, what it does is you can take a shaft here. Let's say that the shaft isn't long enough. Okay, you can put one shaft in one side and then take another shaft in the other side, and bingo, it has coupled the 2 shafts together like that. This is a coupler. So we're going to use couplers not as couplers, but we're going to use them as spacers, because if I have a creation like this, okay, see how it can slide back and forth, and I don't want it to slide back and forth. So what I've done is I've taken a coupler and I've squished it down so it's skinnier than it needs to be, and I just put it here. It stops it from sliding back and forth. So we're going to use it for that. Okay, so what you're going to need to do for tonight's homework assignment is go to Canvas, download these STL files that I have put on Canvas for you, and then you need to make a creation that looks something like this, okay, with gears and sport things. So here's just a note to myself. So I'm going to switch to the browser right now. So give me a sec to change my screen. So instead of sharing the PowerPoint, I'm going to share my browser. Okay, all right, good. Okay, so what you're seeing right now is Tinkercad. Right? So I need to I've got a bunch of windows on my screen that are making it problematic for me. Let me get them out of the way. Okay. All right. So what you're seeing here is a creation that I made last night, where I took these pre-made gears and I made a little support for them. This is the red thing that you see here is the support. Okay. And I put some holes in the support. So let me zoom in on one of the holes there. Okay, you see how so I drilled a hole in the support so that the shaft can go through there. And this gear fits on that end of the shaft. And on the other end of the shaft, I've got the big gear here. All right, see how that works? Okay. And over here, what you see here, this is a handle which I created from scratch using Tinkercad. The red support that you see is something that I created from scratch using Tinkercad. And then this blue piece that you see over here, that's what I'm calling the output flag. Okay. So hang on just a second here. So let's see. Okay, get prepared. You're going to see my face jump. Yeah, sorry. Is that scary to see my face so big? I should have warned you before I did that. Okay, so what you can see here is with the real world creation here, if I turn the handle, do you see how this thing over here, this is what I'm calling the output flag, you see how it turns, but it turns a lot more slowly, okay? I have to turn this handle a whole bunch of times before the output flag will turn even one time, okay? So what you're seeing right here in real life, okay, I want you guys to CAD it up, okay? So let me go back here and go back to share my screen again here. Okay, all right. So now the question is, how did I do this? All right, well, tell you what, let's go to a, let's see, wait a minute. I lost your comments here. Hang on a sec, I need to get the chat window back up. Okay, so if anybody makes a comment, I want to be able to see it. Okay, so I'm going to go back to the Tinkercad dashboard. I'm going to start off with a brand new blank drawing. So this is what you guys are going to do for your homework tonight. So I'm going to create a new design. Okay. All right. Okay, so now I want to import these objects. So now first you have to have gone to my website or gone to Canvas and downloaded the STL files. They have to be on your computer before you do this. Okay, brave job on. Yeah, don't you love those names there? Okay, so now I'm going to come up here where it says import. So I'm going to click on import. And I could import from URL. I could just go to Thingiverse or GrabCAD and type in the URL and it'll pull it from there. But in this case, we're going to assume that you've gone to Canvas and you've downloaded them and they're on your computer. So I'm going to click on Choose File. Okay, so I've already got it on the place where I need. You might need to go into your search mechanism and you might need to find it. But so let's suppose I want to download the large gear, the one that has 40 teeth. Okay, Lego gear 40 teeth STL, and open that. And it's going to ask me, do I want to scale it at 100%? And it's going to tell me what the dimensions are, the length and the width. Notice the length and width are the same. And now I'm going to import it. And wait a second. There it is. Okay, so it now appears on my work plane. So this is one of these Lego gears. Okay, so this thing right here is not exactly the same, obviously. It's a different size gear, but this is a pre-made CAD file for the Lego gear. Okay, so I've got a big gear now. Let's import one of the smaller gears. So I'm going to go back up here to import. I'm going to do another one. And this time, let's import just the 16 teeth gear, the smaller gear. So I'm going to click open on that, Again, it's going to tell me, do you want to change the scale? Do not change the scale, because if you change the scale, then it doesn't represent reality anymore. They won't fit together. Okay, so now I'm going to click import, wait a minute or two, and voila. Now, you don't see any difference because whenever it imports something, it automatically puts it in the center of the screen. And if you've got something already in the center of the screen, they're going to hide each other. Okay, so what I need to do is I need to move this away. So I've taken the first thing that I imported and I've moved it. This now is the second thing that I imported. And so it's right there. So tell you what, let's move it out of the way too. Let's import them all. Let's just go, I'm going to import all 4 of the gears. So let's get the little gear. Okay, here comes the little gear. There it is. I'm going to move it over here. And now let's get the third gear, the one we haven't yet got. So that one is the 24 teeth gear. Okay. Okay, bingo. There we go. We have all of the gears have now been imported, right? Okay, so now what do we do next? Well, let's import one of the shafts too while we're at it here. In fact, let's import not only the shaft, but also the coupler. Okay, so there's the shaft. We're going to want to import that. And let's move it out of the way. So, okay, and then last but not least, let's import the coupler. You'll see I have a couple extra things here that I did not upload to you guys because you don't need them for tonight's assignment. Okay, so there we now have everything that we need. Okay, so now all we have to do is to take these and arrange them in a form similar to what I showed you. So one thing that I recommend before you do a lot of work is let's figure out how far apart do we want the holes in our support to be. Okay, so let's suppose that we want to take these 2 gears right here and we want to put them together. Okay, so if I put these 2 gears together like that, oops. Okay, let me zoom in on that. Okay, so you see how the 2 gears are together? Okay. Now, I need to know on my support piece. In fact, tell you what, let me back up here. I'm going to make a support piece. Let me just do it. Okay. All right, so I'm going to make a real quick and dirty support piece. So I'm going to take the red box, make me something like this. Okay. Now that's a lot thicker than I need. So what I'm going to do is I'm going to make it kind of skinny. That's plenty. Okay, now I'm going to come back like this. Okay, so I'm going to put some holes in here, and these holes are going to be for the shaft to go through to support the gear. So I need a hole. Okay, so let's bring in a hole. Now I would recommend that you make the hole be 5 millimeters because this shaft here is 4 millimeters wide, 4 millimeters tall. I want a little bit extra room, so I'm gonna make this hole that I just brought in here. I want it to be 5. So if I click here, you see how the numbers appear? I can just type here and put in a 5. Type here and put in a 5. It automatically makes the hole be a 5 millimeter hole. Okay, and now what I can do is I can bring the hole over here. Now I'm just doing it at random. You should think before you actually put it there. Okay, so I've got a hole here and I'm going to make it a little bit lower. So you see my hole clearly goes all the way through, right? Okay, and now if I take the hole and I click on here and then I do group, now you can see the hole actually looks like a hole now. Okay, so I'm going to need another hole over here, but the hole needs to be in the right place so that when I take these 2 gears right here, then it needs to be in the right place. So I need to know what is the distance from the center of this gear to the center of this gear. So here's something that's going to help a lot. We haven't talked about the ruler. Over here on the right side, now it may be hidden by your the video right behind my face right now is a thing called a ruler. And so you might need to move the video in order to see it. So I'm gonna click on the ruler and I'm gonna pull it in here. Okay. And this ruler is kind of a neat thing. If you click on the ruler here, okay, it tells you how far it is to the edges on this object here. And you can move the ruler around anywhere you want. You can put it here, okay? But you see how this object here is 25.75. Okay, so tell you what I'm gonna do. I'm gonna put the ruler, so the ruler is lined up exactly with the box there. Not that I have to, okay? All right, so if I click on here, it tells me this. Now you see this option down here, when I hover over it, it says use endpoint. I don't want to use endpoint, I want to use midpoint. Okay, so when I say you click on use midpoint, you see in green right here, when I have to click on the object, you see it tells me that the midpoint of this gear is 25.78 millimeters from the edge of the ruler. So write that down, 25.78. Now I'm going to come over and I'm going to click on the big gear. Now you can see that it tells me that the big gear, actually, wait a minute, let's see. Oh, I'm sorry, 25.78, that wasn't the midpoint, I'm sorry, wig point, okay. The 13.11 is to the midpoint. Okay, so from this edge of the ruler to the midpoint of that gear is 13.11. Don't worry about the negative. Okay, all right, so now write that down. So 13.11 millimeters to the midpoint of this gear. Now if I click on this gear, you can see that it's 46.07 to that one. Okay, so let's see, where did my calculator go? Hang on while I go get my calculator. Okay. Sleep, yeah, okay. All right, so what I'm going to do is I'm going to take 41.87 and I'm going to subtract 25.78. Okay, and what I get is 16.09. Okay, so what that tells me then, oops, let me back up here. Okay, so when I come back here to this guy, when I put another hole in here, I need that hole to be 16 millimeters to the right, if these are the gears that I'm going to use. Okay, so let's take my ruler here. Let's bring this ruler is a really handy thing. I'm going to take the ruler and I'm going to move the ruler over to here. Okay, and let's make it so that the ruler lines up with the edge. Actually, I can. It doesn't really matter where I put the ruler. Okay, so I'm going to put the ruler there, and I'm going to come back here, and I'm going to ungroup these guys. Oops, that wasn't what I wanted to do. This command right here, the undo command, is really nice. Let's take this, and I want to ungroup it, is what I want to do. Okay, so now, if I click on this, it tells me that from the edge of the ruler to the midpoint of my hole is 13.50 millimeters. So what I want is I want my second hole to be 16 millimeters to the right of that. Okay, so what I'm going to do is I'm going to take, oops, so I'm going to take 31.5, I'm going to add 16 onto that. Okay, so 47.5, that's where I want my second hole to be. Okay, so let me back up here. So I'm going to come over here, I'm going to grab a cylinder, I'm going to bring it in here. I'm going to change the dimensions of the cylinder so that it's going to be a 5 by 5, so diameter 5. Okay, let me zoom in a little bit here. Now I'm doing this pretty fast, and I'm going to give you time. This homework assignment that I'm giving you right now is not due on Wednesday. It's due on Friday. I'm giving you time here because I know it's going to take you a while to figure it out. So I'm going to, oops, I didn't want to do that. Okay, so I'm going to grab this, if it'll let me, I need to zoom in a little bit more. Sometimes when you try to grab something, if you're not zoomed in a lot, it's hard to grab it. Okay, so I'm going to grab it and I'm going to bring it down here. Okay. And okay, so I want this hole to be 16 millimeters to the right of that guy. So the first thing I do is I select both of them and I go and I align it. And I want the middles of them to be aligned. Okay, so if I come over here, you see that? Okay, so this guy and this guy, and click on the black one in the middle. So the middles of these guys are now exactly aligned. And you can see the distance between them is 32 millimeters, which is too much. So what I want to do is I want to bring this guy over. Okay. And if you look on the ruler here tells me that it's 52.5 from there, from the edge of the ruler. I wanted it to be 47.5. So let's bring it over here until it's 47.5. There we are. Okay, so now I know that there's 16 millimeters between these two. Now, when I moved it just then, I might have accidentally, in fact, let me do it on purpose here, but I might have accidentally made this guy be a little bit too high. Okay, and so they're not aligned anymore. So what I need to do is I need to realign these guys. Okay, so there you go. So now I have two holes. Let me move this guy down a little bit. Okay, let me move him down. Okay, so they go all the way through now. Okay, so what I've done now is I've created an object that's going to have two holes in it. So I'm going to, let me go do that again. So I'm going to click on one hole. I'm going to click on the other hole. I'm going to click on the red object. I'm going to group them together and bingo. Now, I now have an object that has two holes in it, and these two holes are just the right size so that I can take this shaft now and I can put the shaft through the hole. Let me center this thing here. Okay, you can see my shaft didn't quite go through the hole the way I wanted. So I'll just move it over a little bit. Ah, okay, interesting problem. Look at this. It's snapping to the grid and it won't let me snap where I want. So I'm gonna change my snap grid here so it snaps at a half a millimeter than a whole rather than a whole millimeter. And there you go. Now I can put it so now it fits in the hole exactly the way I wanted it to fit. Okay. And so now what I'm going to do is I'm going to back off. I'm going to push it down a little bit. Okay. And so now you can see that I've got a shaft going through the hole. Okay. So I realize I'm going, did I say 31.5? So I got my number wrong? Okay, that's possible. Don't worry about the number. Let me just finish what I started, even if the numbers are a little bit wrong here. Okay, so what I'm going to do now is I'm going to take everything that I've just created, at least down here. So I'm going to click here, I'm going to drag down there. I'm going to temporarily group that all together. And I'll come back and I'll ungroup it later, but I want to temporarily group it right now. Because what I want to do is I want to lift it up. So let me click it here. I'm going to rotate it 90 degrees. I'm going to lift it up. Okay. All right. And now let me ungroup them. All right. So now I have an axle going through one of the holes. What I can do now is I can take one of my wheels here, one of my gears. And now when you move it around, be very careful. If you move it around and you accidentally grab one of these, you've just messed it up. So if that happens, don't worry, come back here to undo and it'll fix it. So I'm gonna bring my gear over here. I'm gonna center in on it. And I want to rotate it 90 degrees. And then I'm going to lift it up. Now I'm going to bring it over here. Okay. And you can see I need to lift it up a little bit more. Okay, so I'm lifting it up. And now I need to come over here and see, make sure that it lines up with the shaft the way that I want. Okay, move it over here. Okay, so you see how this works? So getting these guys lined up is a little bit tricky. I'm zoomed in too much here. Okay, so you can see there, okay, you see the shaft there? Okay, so I've got the gear on the shaft, except the shaft isn't quite long enough, so no problem, I'll just make it long. Okay. Oops, I made my shaft too short when I did that. Okay. 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 I had to undo what I did here. Let's do it this way. If I take my shaft here, if I click on that guy, I pull it out here. There we go. Okay. So now you can see the shaft goes through the gear. So the gear is in place. Okay. All right. So I went through that really, really fast. But don't worry, it's being recorded, so you can go back and you can watch it again. All right. So I've placed one of the gears on here. And now all I need to do is take the other gears and place them on here. And let me go back to my PowerPoint presentation now. Go back to here. We're almost done, by the way. Those of you that are getting worried that we're running a little long. Normally, I like these to stay less than an hour. Today's is going to be a little bit longer than an hour. Okay. So did I click on the wrong one here? We go back to, okay, here we go. This is the one that we should be on. Okay. So now let's summarize everything that you need to know. So like I said, the assignment that I gave you today is pretty complicated, so I'm giving you some extra time. It's not due on Wednesday. I'm going to give you the whole week to do it. Now, I realize that some of you are going to sit down and you're going to do it this afternoon, okay? But the rest of you got till Friday. So what you see here is what I created, and I don't want you to copy me, but I do want yours to be similar to mine. So you can see I've got the big gear here, and on the other end of the big gear here, I've got a handle that I created from scratch. And so the idea is when I turn the handle, it's going to turn the big gear. Now I've got my other hole here, and on this other hole, I've put another shaft. And in my example here, I put the very smallest gear right next to it. So the very smallest gear is interacting with the very biggest gear. Okay. I don't want you to copy me. So for this gear right here, let's call this gear number 2, and this is gear number 1. So I took the 40-tooth gear and combined it with the 8-tooth gear. I want you to pick different gears, okay? But now this axle up here, this axle here, I'm calling axle number 1. I'm calling it the drive shaft, the drive axle. This axle here is the intermediate axle. Notice it's got 2 gears on it. Axle number 1 has 1 gear and a handle. Axle number 2 has 2 gears. And then over here, you can see I've got axle number 3. It has 1 gear on it. And on the other hand, it has something that looks like my handle, only it doesn't have a little thing for me to grab. I'm just calling it the output flag. Okay. So on the real world example here, okay, this is my drive handle. And then this other guy over here, he's the output flag. Okay. All right, so the thing that I want you to create needs to have 3 axles, and you need to take the 4 different gears, and you need to put those gears on the 3 axles, similar to what I've done here, but don't copy me exactly. Put the different axles in different places. Now, the coupler here is important because, as you can see on the real world example here, If this coupler wasn't there, you see how that thing slides back and forth, and we don't like that? Okay, so what I've done is I've put a coupler on there, but he's not really acting as a coupler. All he's doing is he's acting as a little spacer to prevent this guy from sliding back and forth. Okay, so I want you guys to do the same thing. Take the coupler that I gave you, which is going to be too long, and just squish it down. Okay. All right, and so then put your gears on there, put a handle on it, put an output shaft on it. And so from the one side, it's going to look something like this. And now here's the last thing that I need to tell you, and then we'll be done for the day. Okay. I want you to calculate what the ratio is going to be. So like, for example, on this guy right here, on my real world Lego thing, you see here, if I'm going to turn the handle and I'm going to look to see how many times does the output thing turn. Okay, let's see, I've messed up my, hang on a second here. I got to use the right gears. Okay, all right. So take a look at this. So I turned the handle once, but the output did not turn once, it turned a lot less. So I have to turn it twice, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times. So I had to turn this handle 9 times before this guy turned once. So the gear ratio for my combined thing here is 9. Tell you what, you know what I'm worried about? Today's lesson is running a little bit long. And I'm worried that I'm overwhelming you with too much stuff. So for between now and Wednesday, what I want you guys to do is just try to calculate or try to create your gear thing. Don't worry about calculating the gear ratio. I'm worried that I'm overwhelming you with too much stuff for today. So if you want, this thing here tells you how to calculate the gear ratio. If this guy has 40 teeth and this guy has only 8 teeth, then 40 divided by 8 is 5. So that means for every time this big guy spins once, the small guy is going to spin 5 times. And then if I go and the multiplication factor is 5. Don't worry about understanding what I'm saying now. I'm just going through it really fast. So now I'm looking at it from the back side. So here I've got a 25 teeth gear pushing with a 16 teeth gear. So the ratio there is 1.6. So it means every time the big guy goes around once, the small guy is going to go around 1.6. Okay, so the multiplication factor for these two guys together is 1.6. Now, if I take the two of them together, so these gears up here have a multiplication factor of 5, but that is combined with these guys that have a multiplication factor of 1.6. So the total multiplication factor is these two multiplied. Okay, so what that means is with the gears arranged the way I've got it right now, I have to turn this drive handle 8 times, 8 complete revolutions before the output flag is going to go once. So the overall multiplication factor for my gear thing is 8. Okay, now, what I want you guys to do is I want you to create an STL file, and I want to see your support thing. You know, you're going to create something that looks going to look something like this, and it's going to have 3 holes in it. So I want you to create that, and then I want you to put the gears on it, and I'm going to want you to download just the. I want you to give me an STL file of just your support structure by itself, so that I can see that, because the support structure is something that you're going to have to create from scratch. Okay, so like I said, you may find that the ruler function of Tinkercad is very helpful when you're creating this. Okay, so now let's just summarize what it is that's due on Friday. Remember, you've got the whole week to do it, and on Wednesday, I'll come online and I'll help you, anybody who's having problems. So the first thing you need to do for Friday is to CAD up the gear train, and you have to export the complete assembly of the gear train plus the support structure, export that as an STL file and upload it to Canvas. But I also want to see only the support piece. the thing up here, this support piece right here, I want a separate STL file so I can see that all by itself. Okay. So you're going to upload 2 STL files by Friday. One is the gear train with the support thing. You're going to save that as an STL file. The other one is only the support piece. Okay. And then I want you to calculate the gear ratio. Now, I went over that really fast, and I wouldn't be surprised if you didn't fully understand that. So how about if we come back on Wednesday? On Wednesday, we'll talk more about calculating the gear multiplication ratio. So by Wednesday, if you don't have the gear ratio calculated and you don't understand that, don't worry. We'll come back on Wednesday and we'll talk about it. Okay. So my intention is on Wednesday, I'm not going to cover any new material. What I'll do is I will come on live, and I will be on at least from 11 until 11:30. Now, if you guys have lots of questions, I'll stay past 11:30. I'll stay as long as we need on Wednesday, so that I'll answer all of your questions. And on Wednesday, we'll talk more about the gear ratio and how to calculate that. So between now and Wednesday, if you don't want to worry about the gear ratio, don't worry about it. Just try to create your gear box. There will not be a quiz on Wednesday, okay? But there will be a quiz today, just to make sure that you guys understand what the assignment is. So I'm not going to do any secret words today. I'm just going to, the quiz questions will be just to make sure that you understood what Friday's assignment is. Okay, so I went over a whole lot. I would not be surprised if you guys have lots of questions. Let me pause right here. I'm not seeing any comments. So give me yays or nays. Okay, now, can you use SOLIDWORKS? Yes. So Luke and Mason and anybody else who understands SOLIDWORKS, yes. If you want to use SOLIDWORKS for this, you can. The CAD files that I put on Canvas, you can import them into SOLIDWORKS just as well as you can into Tinkercad. Any other questions? No question. I'm actually surprised there's no questions, because I took a lot of stuff and I compressed it into a small bit of time there. So I highly recommend that you go back and look at the recorded video, and then just pause it periodically. That'll help. No secret words today, David. Sorry. Today, the quiz is all going to be about, do you understand what the assignment is that's due on Friday? Now, don't forget the CAD competition that I talked about last time. The Robotics Club is having a CAD competition. The challenge is to use CAD to create a writing instrument of some sort. The more fancy you are, the better the chances of winning the CAD competition. Submissions are due by Saturday at midnight, and I will give you extra credit if you participate in that. Okay, so any questions before I turn off the recording and end the class? Last chance. Going once. Not seeing any questions. Going twice. Nope, no secret words today. Okay. The quiz is all going to be about making sure that you understand the assignment. No secret words today. All right. Well, in that case, no more questions. So I'm going to end the recording.